Hey, everybody. So today in class, we talked about several different things. Uh, the main thing was mass, atomic mass, and then I gave a little worksheet that was, which is posted on Classroom. Oh no, it isn't posted yet. I'll post it. Well, by the time you see this, it will have been posted. I gave a hard copy of it in class. I'm posting an electronic copy online. And so I'll try to explain. Um, oh gosh, that means I got to find it. I may have to pause this video and see if I can find it. Anyway, first thing we talked about, after the elements quiz, which hopefully you studied for, average atomic mass versus mass number. On the table that I gave you, in every, pretty much every periodic table of the elements, there is something called average atomic mass that's shown. And average atomic mass is different than what we've been calling mass number. All right. So mass number is the proton plus the neutron. Okay. Proton plus neutron is mass number. That's what we've been saying all along. Like, how do you find out the mass of an atom? You add up the protons plus the neutrons, and that's the mass number, which is what we've been saying. We've kind of ignored the fact that in the table, in the periodic table, there are average atomic masses that are not whole numbers. If you add protons plus neutrons, you're only going to get whole numbers. The average atomic masses in the tables are not whole numbers. And so the question is, why is that? Why do we have masses in the table that are called average and they're not whole numbers? Well, it's kind of like this. Here's how this works. Let's look at boron. Okay. There is boron 10. Whoa, that O got kind of, there we go. So there's boron 10 and there's boron 11. What does that mean? Well, the 10 and the 11 are the actual mass number. So there's boron atoms that have a mass of 10, and there's boron atoms that have a mass of 11. The average mass for boron is 10.81. Average mass is 10.81. But some of them, some boron atoms have a mass of 10, some boron atoms have a mass of 11. Now, question, how many protons do those boron atoms have? How many protons do those boron atoms have? I hope that in your brain you're thinking about the fact that they both have 5. Both of those boron atoms have 5 protons. I hope you're writing all of this down. Like, this is like notes. This is what we did in class. So both of those boron atoms, a boron 10 and a boron 11, they both have a mass, or they both have 5 protons. Otherwise, it wouldn't be boron. Boron has 5 protons, all of them, or it's not boron. Now, how many neutrons does boron 10 have? Well, if it's 5 protons plus 5 neutrons, which gives you a mass of 10. That means that boron 11 has 5 protons plus 6 neutrons to make a mass of 11. And that's exactly how it works. Okay. Now, here's the question. How can 10 and 11 average out to 10.81? That doesn't seem to fit. How can 10 and 11 average out to 10.81? Now, I hope you're thinking through this and thinking about the fact that that means that there's more what than what. There's more boron 11s out there than 10s because the average is closer to 11 than it is 10. It's kind of like this. Let me move myself over here. I made a little list here. Let's just say, come on now. Let's just say we took a quiz. There's 10 kids in a class. We took a quiz, and 9 of them got 10s, but 1 person got a 1 out of 10. So what's the total here? 10, 20, 30, 40, 50, 60, 70, 80, 91. So 91 is the total. If we were going to average this value. So that's a 91 average. I mean that's a 91 total if you add them all 10 scores. Divided by 10 scores, and that means your average was what? 9.1. So this 1 down here changes the average a little. It's not like the average is in the middle between 10 and 1, because all these 10s weight the average toward 10. So your average is actually 9.1, not like 6 or 5.8 or something like that. It's not halfway between 10 and 1, if that makes sense, I hope. So the average is weighted toward what there's more of. So if you think about boron here, let's say we have 4 boron 11s. Let me get myself back in the corner here. 4 boron 11s and then 1 boron 10. That's 54 total, divided by 5 atoms. That's 10.8. Oh, so we've got about a 4-to-1 ratio here. There's about 4 boron 11s for every 1 boron 10-ish. That's how the 10.8 could be an average, even though there's only 2 kinds of borons. Now here's the other thing. Are these 2 kinds of borons any different than each other? Not really. The only difference is one of them has 1 more neutron than the other. They have the same number of protons. They're both going to have 5 electrons because remember, the electron number and the proton number are the same, so they're balanced charge-wise. So the only difference between these 2 atoms here is the number of neutrons. Now, and this is the way you'll see it written. How I've written this right here, boron dash 10 and then boron dash 11. Or I could write B dash 11 and B dash 10. That's telling you which kind of boron atom I'm talking about, because again, they don't have the same mass. That's called something. That has a specific name, and it's called an isotope. Okay? This is a term you need to know. An isotope, those are atoms of the same element with different masses. Same element. Atoms of the same element with different masses. So there's a boron that has a mass of 10, and there's a boron atom that has a mass of 11. They're both isotopes of the boron element. Now, again, the only difference between them is that they have a different number of neutrons. Their masses are different because of a different neutron number. The proton number can't be different or it's not the same element. Okay? Same element means same number of protons. The neutron number is the only thing that can be different. Now, another example, carbon. Carbon is another example, and there's 3 different isotopes for carbon. There's a 12, 13, and 14. Now, how many protons does carbon have? Hopefully you know that carbon is number 6 on the table, and therefore it has 6 protons. Each of them has 6 protons, which means that carbon-12 has 6 neutrons, carbon-13 has 7 neutrons, and carbon-14 must have 8 neutrons. So that's how that works, right? And those are all 3 isotopes. It's not like one is normal carbon and one is weird carbon. Now, some are more common than the others, but all 3 of them are considered isotopes. It's not like one of them is normal and the other 2 are isotopes. All 3 of them, they are all atoms of the same element with different masses, which makes them isotopes. That's isotope, that's an isotope, that's an isotope. They're all 3 isotopes. That's what it's called. Now, the average mass for carbon is 12.011. If the average mass for carbon is 12.011, then what does that tell us about these 3 isotopes? Hopefully you can tell that that means that carbon 12 is much more common, that 13 and 14 are way lower in prominence in a sample of carbon. If we were just to have a sample of carbon, like what we used in the element lab, the pencil lead, like the lead that's in your pencil, most of those carbon atoms are carbon 12s. And there are some carbon 13s and some carbon 14s, of much smaller percentage of them. All right, moving on. Another one is chlorine. Chlorine's average mass is 35.453. Is there any way you can tell me what chlorine's isotopes are by looking at the fact that the average mass is 35.453? Is there any way you can tell me what chlorine's isotopes are? The answer to that is no. You can't tell me, because there's a bunch of different ways you could get an average of 35.453. A bunch of different ways. Maybe 35 isn't even one of them. Maybe 36 isn't one of them. Maybe one of them's 40. Maybe one of them's 30. Like, we have no way of knowing what they are. And you won't have to be able to determine that. Right? I can't ask you, hey, what are all the isotopes for X element? Unless I tell you what those are, then make you memorize them, which I won't necessarily do that. Okay. So, but there are two. There are two for chlorine. And let me tell you what they are. So there is chlorine. Oh, I guess when I reveal it, I have to reveal the whole thing. We know that there are 17 protons in all chlorine atoms because chlorine is number 17. For chlorine 35, there has to be 18 neutrons because 18 plus 17 equals 35. And for chlorine 37, there has to be 20 neutrons because 20 plus 17 is 37. So I hope that you see that if I ask you how many neutrons one of these isotopes has, you should be able to tell me. Again, it's the mass number minus the proton number, and that tells you how many neutrons there are. Again, these two have to add up to the mass number, which tells you what isotope it is that we're talking about. All right. Now, what do these two values tell you about, or I should say, what is the average here, 35.453, what does that tell you about which one of these is more common? Hopefully you can see that 35 must be more common because the average is closer to 35 than it is to 37. If the average was 36.0 exactly, then what would that tell us? If the average is right in the middle between 35 and 37, then that's telling us that the average, or that there are equal numbers of 35 and 37. They appear in nature equally, but they don't. There's more 35 than 37 because the average is weighted toward 35. I hope that makes sense. Let's see, what else do I have in here? Oh, here's the thing about, here's the numbers that we're talking, the 35 and the 37 and the 12 and 13 and 14 and the 11 and the 10, all of those are a measure called an atomic mass unit. So it's 37 atomic mass units, or AMUs as we call them. All right. Now, what is an AMU? It is defined as 1/12 of a carbon 12 atom. That's what 1 AMU is, 1/12 of a carbon atom. What does that mean? That means if you take a carbon atom here, if you take a carbon atom, a carbon 12 atom, let me get this out of here. If you take a carbon 12 atom, 1, 2, 3, 4, 5, 6 neutrons, 1, 2, 3, 4, 5, 6 protons, and 1, 2, 3, 4, 5, 6 electrons, that is a neutral carbon 12 atom. If you take the mass of that whole thing, divide it into 12 pieces, that's what 1 AMU is. And then we say, for ease of discussion that one proton has a mass of 1 AMU and that a neutron has a mass of 1 AMU. And so if you just add the two of those particles together in an atom, that tells you the mass. It's as simple as that. And then this part here, the unit symbol for an AMU is a lowercase u. So if you're told that an atom has a mass of 55 U with the lowercase u, that means 55 atomic mass units. Just like G, little g is the symbol for gram, just like kg is the symbol for kilogram, or lb is the symbol for pounds, U, lowercase u, is the symbol for an AMU, or atomic mass unit. Just in case you see those things around, if you see AMU shown somewhere or listed, or you see lowercase u used as a unit symbol, they're talking about atomic mass units. So that's what we talked about in class today. Then I gave the sheet, which is it's on Classroom. It is the electron energy level worksheet. And what you have to do is, and it should be horizontal. And I don't know if you're not in school right now and you're out of school, I'm not sure exactly how you're going to do this. I don't know if you can load this into DocHub, or if you can draw somehow on a PDF file. That's how you would be able to do this electronically. You have to be able to draw on the PDF. So if you can get into DocHub and open this PDF file in DocHub, that would be the way you could do this electronically. Otherwise, you'll have to have a hard copy of this worksheet. Let's see if I can actually find this worksheet. Hold on. Finder. Document. Oh, no, that's not it. Documents. Modeling content. Electron. Oh no. There it is. Yep. This is it. Okay. And again, it's sideways. How can I turn it? Can I turn it? Oh, I don't even know. So the way this is, you have a map down here with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the order that you will place the electron dots in these little models based on, I guess I can write on here. Let's see, with a pen. So for instance, for hydrogen, if we're looking at hydrogen, hydrogen has how many protons? 1. So in the nucleus, which again, the nucleus is just showing as a black dot. It doesn't even have to be, like, we're not talking about the nucleus right now and how many particles of each are in the nucleus. But the directions say that you're supposed to draw the correct number of electrons in the element's corresponding energy levels using the general map of valence electrons, which is this right here, the valence electron map. And it says, assume that all elements have a net charge of 0. Now, what does that mean? They have a net charge of 0. That means the proton number and the electron number have to be what? Now, this goes way back to when we first were doing atomic structure. For the net charge to be 0, the proton and the electron number have to be equal. Hopefully you remember that. So if hydrogen has a single proton, then that means it has to have a single electron. And I would draw in here, is it letting me? Oh boy, yeah. Oh boy, that's horrible. So I put my little dot there. Why there? Because that's where the number 1 electron has to be. The number 1 electron is right there in the number 1 spot. And so that's where I put it. Now for helium, which has how many protons? 2. So then you're going to have to draw dots where there's not just 1 electron, there's actually the second electron. And so those are the 2 locations of electron number 1 and electron number 2. That's where they go. Then you'll go over to lithium and you'll again do the same thing. How many electrons does it have? And then you're going to have to sketch dots on the atomic model in the correct area. Again, we have the first energy level, which holds 2. We have the second energy level that holds 8, and then we have the third energy level, and then we have the fourth energy level even outside of that. So you'll draw dots that represent the electrons, and then for page 2 here, which technically is worksheet number 5, atomic structure, you'll answer these questions about what you had just done drawing the electrons. So that's what you're supposed to do. If you're not here, this is what I told everybody in class. Hopefully you can find a way to open up this and draw on it electronically, and then you'll have it ready to go. You can even change the colors, I guess. Let's see, what if I do this, if I just do a single click, does it show up? No. I have to move it around? No, that didn't work either. Oh, it's drawn a, what's happening here? I just want the pen. Can I, there, I drew something. Draw another one here. There we go. Oh, look at that. They're messy, nasty blobs, but at least I drew something. Okay, so do that. I'm going to actually post it as an assignment. You can load your the PDF file if you save it as a PDF from DocHub, or however you've edited it and saved it, do that. Otherwise, you'll have to take a picture of your work from the physical paper if you have the physical paper, and then, yeah, we'll go from there. So test. We're planning on a test. So for B1, the test would be on next Tuesday on this whole unit, from atomic structure all the way to the stuff we're going to get done the next 2 days. That test is going to be next Tuesday for the B1, next Wednesday for the B2. So be thinking about that. Test next week. All right, I'm finally done. This is too long. Goodbye. Good luck. Have a great day. Stay safe.